Now let's have a look at problem 9.2. We're given a first order system here where W of t and V of t are the process noise and the measurement noise respectively, and the statistical properties of these noise signals are given here. Note that a delta of tau is missing here. We're supposed to find a controller K of S that minimizes the LQG cost, and remember that this LQG cost is nothing but this one under some statistical assumptions. So let's have a quick look at what the tasks are. We're supposed to first draw a block diagram of the controller K of S, so basically the structure of K of S, then find the optimal estimator gain Fe. For a given optimal value of gain F, we're supposed to find the value of rho for which the given F is optimal, and then for a specific value of Re, write down the closed loop dynamics and check if the error dynamics are faster, or the estimator dynamics are faster than the sort of control dynamics. And finally, we're supposed to compute this quantity here. So let's start. Let's first draw the block diagram of the complete system. So we have 1 over S, 1, this is C, which is also 1, then we have P, which is also 1, and then we have process noise here, and we have measurement noise here, and this is Y, this is X dot, this is X, this is U. Now inside the controller K of S we have a copy of the plant, but because we cannot measure the process noise or the measurement noise, we just take the difference between the y hat and the y. So this is x hat dot, this is x hat, and we have an estimator gain Fe coming like this. So we, to this copy of the plant, we provide the same input U, which is computed by the gain F multiplied by the estimate x hat. So in the design problem, we're supposed to design Fe and F. Let me draw the arrows here. Fe and F, so that we have minimal LQG cost. Now, we've seen in the lectures that we can do this by solving two independent problems. The first one is the LQR problem. So that is assuming we have complete state measurements. We solve the LQR problem by solving the algebraic Riccati equation and get the value of optimal gain F. Similarly, we can solve the estimation problem and get the optimal value of Fe and just put these two things together. So that is what we will do now. So first, let me draw um, the block k of s in this block type. So k of s is this block. So in a compact form, we can write g of s as our plant, on which we have the process and the measurement noise. Y is the output, and then we have k of s giving us u. So that was part A. Now, in order to come to B, let's quickly review the two Riccati equations. So we first solve an algebraic Riccati equation to get optimal f, and we solve a filter algebraic Riccati equation to get optimal fe. So for this one we need a, which is 1, b, which is also 1 from the plant. We need the weight on the control cost rho, and we need q, which is typically 1. So this one is nothing but r, which is called rho for the single input single output case. So the algebraic Riccati equation is then a dp. So I will just write the final thing down. Equal to 0. So we have p squared minus 2 rho p minus rho equal to 0. So once we have the p, we can compute the optimal gain as minus r inverse p transpose p. So minus 1 over rho, b is just 1 p. So that is the solution to the LQR problem, where we assume that we have perfect state measurements. Now for the optimal estimation problem, we solve the filter algebraic Riccati equation. We need here A transpose, which is 1, C transpose, which is also 1, QE, which is 1, and RE is just called RE here. Now the filter algebraic Riccati equation is again nothing but 2PE, which is still the same. So we get basically the same result, only with RE replacing rho. And then the optimal estimator observer gain Fe is given again by this expression. So this was part B. Now in part C, we are asked to find rho for which f equal to minus 3 is optimal. So let's first solve the ARE, the algebraic Riccati equation. So P in this case is given by 2 rho. I'm just using the quadratic formula here. Divided by 2. So I can cancel the 2 and I can pull out the rho to get. Now note that the stabilizing solution to the algebraic Riccati equation is the one which is positive definite, in this case positive because we are just scalars. So P equal to rho times 1 plus square root of 1 plus 1 over rho is the optimal, is the solution that is positive definite, and then f star is nothing but minus 1 minus 1 over rho. Now we're given that f star is minus 3, which is minus 1 plus 1 over rho. So we have 1 over rho equal to 2. So rho equal to 1 over 3. So this is what is asked in C. Now in D, we are given a value of Re which is 0.125, and we want to find the optimal gain Fe star. So first let's again solve Pe as a function of let's first solve the filter algebraic Riccati equation, and because the equation is identical with the algebraic Riccati equation, we can just write the solution here by replacing rho by Re. And so Fe so now we can substitute the value of Re equal to 0.125 to obtain so that's 8. So we have 9, square root of 9 is 3, 4. So we obtain Fe star to be 4. So now we are supposed to write down the closed loop dynamics. So let's do that here. So we have x dot is x plus u plus w, and y is x plus v, so that is the plant. We have the estimator dynamics as x dot is x cap dot is x cap plus u plus fe times x cap minus times y cap minus y, which is then nothing but x cap plus u plus fe times c x cap. C is just 1, so x cap minus x minus v, so we get 1 plus fe x cap plus u minus fex minus fev x cap, and then we have the control input u equal to f times x cap. Substituting this u in both the plant and est, so these are the plant dynamics and these are the estimator dynamics. So substituting this u equal to f x cap in both, we get x dot is x plus b, so b is just 1, so plus f x cap plus w, and x cap dot is 1 plus fe x cap plus f again x cap. So I combine this term and this term in one bracket minus fe x minus fe v. So now having this, I can just write down the error dynamics by defining error as x minus x cap, and then E dot is just subtracting equation 2 from 1 to obtain one plus fe x so so that can be written as, so that's minus here, that can be written as fee plus w plus fev. So the error dynamics are these first order dynamics with the pole at 1 plus Fe, which is nothing but 1 minus 4. I think Fe was minus 4, so 1 minus 4, which is minus 3. So now the control dynamics places the poles at 1 plus F, which is 1 minus 3, which is at minus 2. What we ideally would want is to place the estimator poles much further to the left than these poles. So if we want to have at least 5 times faster estimator dynamics, we need the closed loop poles of the estimator to be at minus 10, so 5 times minus 2, which means that Fe should be minus 11. So obviously with Fe minus 11, the error dynamics would be minus 10E plus W minus 11V. And the last subproblem is then to calculate expectation of theta of t, where this is defined here. So we can try to compute this. We get this is nothing but now taking expectation is a linear operation, so we can, so what I mean is expectation of x plus y is expectation of x plus expectation of y. Furthermore, expectation of m times n is expectation of m times expectation of n if m and n are independent random variables. So we will use these two things to then write this as expectation of, so I will now just simply write down based on the statistical properties of W, the first term would lead to Q E delta of tau. The second term and the third term would go to 0 because expectation of W times V is expectation of W times expectation of V, because V and W are independent random variables, and expectation of V is 0, and so is expectation of W 0. And the last term will give us RE delta of tau, which is nothing but QE plus 121 RE. And that's it for this problem. Thanks a lot.